Good morning, afternoon, evening, or whatever time you're watching this. My name is Jordan Smith, and today we'll be going over our second physics lab, demonstrating motion of a falling object. Before we go into this lab, there are a few fundamental formulas that we need to know. But more specifically, there's one that we haven't already covered in our previous lab. To start, here is our first fundamental formula, the momentum principle, which states that the net force is equal to the change in position over change in time, or the derivative of position with respect to time. There is also net force equals mass times acceleration, although it will not be that useful in our lab. Using the tracker software, we are able to gather a position versus time graph in the y-axis, almost resembling half of a parabola. We are also able to plot every individual frame of information, totaling 37 frames. This allowed us to create a table showing the position versus time of each step of 0.017 seconds. Using the tracker software, we were able to gather that our observed time is 0 seconds, that our end time is 0.616 seconds, and we were able to set our axis to have our initial position be 0, and our initial velocity was 0 since we dropped from rest. Using our own intuition, we were able to create a computational model. The ball's position vector is at 0, 0, 0. Ball's velocity vector is 0, 0, 0 as well. Time is at 0 seconds. Our delta t's time step will be 0.0165 seconds. And gravity near the Earth is 9.8 meters per second. The ball's mass was computed using a scale, which approximated to this. Carrying on, we know that the balls, after modeling our data, we were able to see that the computational model data and the tracker data are very similar. However, I feel as though we could make this approximation closer. So, what we're thinking is, we didn't account for anything such as air or a typical breeze, kind of like how we were in our previous experiment. But this time, we have an equation that can help us. Now, for our second fundamental formula, drag force. Drag force always opposes the motion of an object. A general formula for drag force is negative b times velocity squared times the unit vector of velocity, or, to be simplified, b times velocity squared, where b is the drag force constant. Now, using that new fundamental formula, we were able to calculate a better net force as shown through lines 69 through 72. But we don't know our proportionality constant. This is where I had to use some intuition. I referred to the video provided in week 4 in order to gain a slight approximation of our proportionality constant. After realizing that that wasn't correct, I adjusted it a few times. Ended up with 0.00139. After using the information from our new computational model, we have a graph that's looking a little bit closer to our tracker information. Finally, we now must ask about a series of what-if statements. Now, let's imagine that the ball was initially thrown downward. We're asking, would the terminal velocity be the same or different? I believe the terminal velocity would still be the same, it would just happen quicker. To prove this, I'm going to attempt to change the initial velocity to be equal to -1 meters per second in the y direction and model it through GlowScript. As you can see, other than reaching terminal velocity quicker, there's really no change.